Dear students, in the last class we have started the third chapter, the tangent space. We have defined what is meant by a tangent space. A tangent space means, suppose we have a function f from an open subset u of Rn plus 1, and this function is smooth, and f inverse c be a level set such that p belongs to f inverse c, p be any point in f inverse c, then a vector at p is said to be tangent to the level set f inverse c if it is a velocity vector of a parameterized curve in Rn plus 1 whose image is contained in f inverse c. Okay, so we have two conditions here. A vector at a point p is said to be tangent to the level set f inverse c if it is a velocity vector. First one, velocity vector of a parameterized curve in Rn plus 1, and second one, whose image is contained in f inverse c. These are the two conditions. So we have seen some examples also. If n equal to 1, then our u is a subset of R2. That means our level set is a curve in R2. So if we take any point from this level set, say P, okay, then the tangent to this curve at the point P is the velocity vector of a parameterized curve which is in f inverse. That means here this is the velocity vector v. Okay, now if n equal to 2, then we have the level set is this one and the parameterized curve is this one, and p be a point in this curve, then the tangent vector at p is this one. Okay, so we have a note: each vector tangent to f inverse c at p is of the form alpha dot of t naught for some parameterized curve alpha with alpha of t naught equal to p and image alpha contained in f inverse. So if f inverse c be a level set and a vector tangent to this level set at a point p is of the form alpha dot of t naught for some parameterized curve alpha with alpha of t naught equal to p and image alpha contained in f inverse. So please keep in mind this condition. Now we have a lemma. The gradient of f at p belongs to f inverse c is orthogonal to all vectors tangent to f inverse c at p. The gradient of f, that means del f of p, is orthogonal to all tangent vectors, all vectors tangent to f inverse c at p. So the proof is very simple. Next, we have a definition of regular point. Okay, a point p in Rn plus 1 is called a regular point if del f of p not equal to 0. Now we have a theorem. Let u be an open set in Rn plus 1 and let f from u to r be smooth. Let p belongs to u be a regular point of f and let c equal to f of p. Then the set of all vectors tangent to f inverse c at p is equal to del f of p orthogonal. The set of all vectors tangent to f inverse c at p is equal to del f of p orthogonal. We have u be an open subset in Rn plus 1 and f is a smooth function from u to r, and p is a point in u and which is a regular point. That means del f of p not equal to 0, and also p belongs to f inverse c. Then the set of all vectors tangent to F inverse C at P. So we have P belongs to F inverse V. Then we have already defined what is meant by a tangent vector at P. So set of all tangent vectors at P is equal to del F of P orthogonal. This is what we want to show. Okay, so we have every vector tangent to F inverse C at P is contained in del F of P orthogonal. We have proved in the previous lemma. Okay, we already proved this one. To prove the reverse part, it is enough to show that if V equal to PV, which is in del F of P orthogonal, okay, we have proved every vector tangent to F inverse C at P is contained in LF of P. Now we want to prove the reverse part. So to show this reverse part, we take V from this del F of P orthogonal. Okay, then we want to show V equal to alpha dot of 0 for some parameterized curve alpha with image alpha containing F inverse. This is what we want to show. Okay, so for this, consider a constant vector field x on U defined by like this: x of q equal to qv. Now from x we can construct another vector field y by subtracting from x the component of x along del F. Okay, so from x we can construct another vector field y. Okay, by subtracting from x the component of x along del F. So we know that suppose we have two vectors a and b, vector a and vector b, then component of vector b along vector a is equal to a dot b divided by mod a into mod b whole into vector a. So by using that result we will apply here. So here we want to construct another vector field y by subtracting from x the component of x along del F. So here the component of x along del F is equal to x of q into del F of q divided by del F of q whole square, norm del F of q whole square. Okay, so into del F of q. So here component of b along a means vector a dot b divided by mod a square into a. So by using that result we can write x of q into del F of q divided by norm del F of q whole square into del F of q. Okay, so the vector field y has domain the open subset of U where del F of del F if not equal to 0, del F not equal to 0. Okay, since P is a regular point of F, then del F of P not equal to 0, and hence P is in the domain of Y. Moreover, we have x of P equal to PV, which is actually V, which is in del F of P orthogonal. So that means x of P dot del F of P equal to 0. Now we take y of P. So y of P equal to x of P minus x of P into del F of P divided by norm del F of P whole square into del F of P. But x of P into del F of P equal to 0 here. So this part 0. So remaining only x of P. X of P is actually V. Okay. So y of P equal to V. Again, y of q dot del F of q, which is equal to x of q dot del F of q minus we have y of q already we have defined here y of q. So y of q dot del f of q equal to x of q into del f of q minus we take dot product with del f of q here. Okay, so we have this. Then here from here we can cancel these two. Then we are the remaining x of q dot del f of q minus x of q dot del f of q. That means equal to 0. That means the dot product of these two vectors is equal to 0. Thus we have obtained a smooth vector field y such that y of q is orthogonal to del f of q. This is for all q belongs to domain of y and y of p equal to v. This is not dim, this is actually domain of y, and y of p equal to v. Okay, now let alpha be an integral curve of y through p. Then alpha of 0 equal to p. Also alpha dot of 0 equal to y of alpha of 0, which is equal to y of p equal to v. This is question number 1. And again derivative of f of alpha of t. That means del f of alpha of t dot alpha dot of t. So alpha dot of t means y of alpha of t. Okay, so we have dot product of this is equal to 0. That means this is f of alpha of t is a constant for all t, belongs to the domain of alpha. Okay, but f of alpha of 0 equal to p, that means f of p which is equal to c. So this implies f of alpha of t equal to c for all t in the domain of alpha. Therefore alpha of t is a subset of f inverse c. So that means image alpha contained in f inverse. So we have proved all the conditions. So and therefore any vector in del f of p orthogonal is a vector tangent to f inverse c. Then the set of all vectors tangent to f inverse c at p is equal to del f of p orthogonal. Okay, now we have a note. At each regular point p on a level set f inverse c of a smooth function, there is a well-defined tangent space consisting of all velocity vectors at p of all parameterized curves in f inverse c passing through p, and this tangent space is precisely del f of p orthogonal. Okay, so at each regular point p on a level set f inverse c, that means del f of p not equal to 0. Okay, there is a well-defined tangent space consisting of all velocity vectors at p of all parameterized curves in f inverse passing through the point p, and this tangent space is actually del f of p orthogonal. Okay, thank you.